Okay, so my talk is at the last does not mean that I have the last word on what has been going on. My only intent is to actually do two things. One is to kind of summarize what has been presented since morning and also add a few more ideas of our own. Myself and Marshall were discussing in the morning, and we were saying that we are now at an age that we have, within our own scope, we have done a lot of things, maybe or not done, but now something that we want to do is to have, a chance to transfer whatever we learned or did not learn to the next generation. So education is our focus. And I think for myself, especially being part of university for now almost 25 years, education just come naturally. But at the same time, I just want to share a little bit personal comments on this time that I have had the opportunity and a good fortune to be in a place where you get to work on all aspects of your profession. For example, you get to, first of all, teach graduate students, and that itself is a very satisfying job. And these are all engineers already, so you get to interact with them. You have to be on your toes all the time. Then you get to supervise the research, on very interesting topics. And when you sit down and you attend the final exam for the students, they have done a year of work, and then they transfer or pour that knowledge onto you in 1 hour. And for no reason, you learn for one year of man input in 1 hour, and you pick the points and you get free learning. So that's great by itself. And then at the same time, I'm also heading the commercial, I would say, arm of the university. So we get to work on the real projects. So we also get to apply what we taught and we learned and we researched onto real projects. And at the same time, learn from what the real projects challenges that have to offer, and bring it back to the research, and then do some more research, and then take it back to the project. And on top of that, also get to work on the development of the tools that the engineers use to do their professional work. And also, and the last minute and most important to me is to get to share that knowledge in our capacity building programs and so on. So it's a very interesting place that I have been. And I think that my today's talk is not about structural engineering, calculations, performance-based design. Talked a lot about that, but it's about education and educating the next generation of structural engineers. And this is something, as I mentioned in the morning also, that myself and Ashraf, we talked about this also a lot, that we should now focus on how best we can develop things or develop content and the delivery method that will help the engineers to solve some of the things that Professor Warsak mentioned in the morning, that we don't have the sense of engineering, we don't get to experience the same way the learning that we did. It's always interesting that every generation is nostalgic about how good their time used to be, and how the new generation is not smart enough or not learning the same way. But this generation has its own sort of, or the next generation coming up have their own way of doing things. All I think we need to do is to understand both sides and try to develop methodologies that can satisfy what we think is valuable and what we believe is the new generation's way of looking things. So my talk is a little bit about those kind of things. So first of all, let me correct, I'm talking about civil and structural engineers. I don't intend to talk about all engineers. Just to be, if anybody has any doubt, it should be clear now. Civil engineers, as we have been all reminded since morning, that we do things that everybody else relies on. Every engineer, either electrical engineers, mechanical engineers, telecommunication engineers, architects, town planner, whatever they want to build, ultimately structural engineers have to build it. It may be transmission towers, it's a transportation network, you need tunnels, you need bridges. Whatever you need, any engineering profession, structural engineers have to be the last person to actually make it happen. So from that point of view, it's a very interesting profession to be in. Now, this is some reading from the ASC's Vision 2025, what they want the engineers to be in the future. So they want them to be innovative and integrator of the whole things. So there's a lot of things that the professional bodies are looking at. So my question is that if you want to be all of that, what is it that we should be teaching to civil and structural engineers, and how we should be teaching so that these visions become reality? So let me look at these two questions. Number one, what is the content that we should be teaching, or we are taught, or is important? And the second related question, how we should be doing that. So the what, so if you look at the what, typically, people in academia refer to this Bloom's pyramid in a different formats. Everybody has its own version of this pyramid, in which they see what kind of abilities or skills or knowledge, or what do we need ultimately the people to learn in their university or later at different levels. And as you can see, the lowest one is remember things. So, I remember when we were young, we were taught multiplication tables, memorize those tables, remembering things. And then our test was only how fast we can write down what we remembered. So that's one. The next level is understanding. Did we understand any of that, what we remembered or what we memorized? So next level is using that memory to understand, then to apply that knowledge or understanding to something, and then to analyze whether that application has been useful or not. And then then that leads to evaluation, analyze, evaluate, and then create new things based on all of that. So the creation is at the top of the pyramid. So this typical or many variations of this Bloom's pyramid you will find in which the outcomes of teaching are assessed. And this is also the basis of a very interesting document which is prepared by ASC, which says Civil Engineering Body of Knowledge for the 21st Century. So they have done this great study and quite a thick book in which they have put down what is it that the civil engineers of 21st century, what kind of knowledge do they need to do what they expect them to do in the vision. And if you look at this table that they have come up with in the end, it actually is an extension of the Bloom's pyramid for learning. And then they divide it, what should be taught in undergraduate, and so on. So if you look at the foundation knowledge that should be taught at a bachelor level, and what kind of skills, or what part of the knowledge, what part of the 6 things that we need to learn, they teach you. You can see mathematics, natural sciences, humanities, social sciences should be there at that time. And they will basically give us the knowledge and the first 3 parts of that pyramid. So with this knowledge, it's mostly the first 3 parts that we will cover. And this should be covered in bachelor level. Next one is the technical. So this is the subject areas of the civil engineering. So first one is a general, broad spectrum knowledge that everybody should get. Then is technical, and then you start to see, topics like, mechanics and experiments and problem investigation and design and uncertainty and all of those things that now relate to applications later. So this is technical, and this may vary from one engineering or one subject to another, and this should also be part of that should be taught at bachelor level, and part of that will be taught at the master's level, and some of it will be learned through the experience or work experience. So this part is the second big part of the learning process. And then comes the last one is the professional level. So professional level, as you can imagine, that some of that will be taught at bachelor, some in masters, and some will be learned as we go along. So they have categorized or listed down what is the curriculum of the civil engineering program should look like if we are going to produce engineers who have all the 6 levels of the knowledge that we are trying to instill on the people in their lifetime. And then based on this one, this is the roadmap from them in which the foundational, technical, and professional knowledge will be developed, through those 6 steps of knowledge, which means basically remembering, telling them what the things are about, then about the comprehension, understanding of the knowledge, what it is all about, and then application, try to see where it is applied, and then analysis, what is the outcome of this application, evaluate, and then create. So this is the typical way the engineers are trained or should be trained, or the programs, academic programs, and the professional programs are designed integrately. So profession and bachelor, and all of that is integrated into one learning experience. And part of that obviously happens in different locations, different phases in one's life, but the total knowledge still needs to be that complete. Based on that, this is one possible model that I was asked to develop for a new school of civil engineering in one of the universities. And this is what we thought that, okay, should the university's new school of civil engineering be doing? As you can see here, the bottom is the exposure to SDGs and environmental sustainability, social responsibility, all of that thing, very basic, and attitude and humanity, all of that we just heard that is so important. And then on top of that we can build the courses, go on, and then go into more mathematics and physics and chemistry, and on top of that more technical oriented, and then vertically then we can have specialized areas which could be in master's degree or different subjects within civil engineering. And one last, on your left, on your right, sorry. On your right is an area which is of quite interest now, is the special areas. That means the application of other technologies and other disciplines in structural engineering. Because as we know very well that now there is a lot of other stuff going on in other disciplines that we can learn from, or we need to bring back to structural engineering to make it as effective as many of the other disciplines are becoming. And obviously that's about IT and software and so many things that we will maybe we will talk about in some detail. So that part is quite important and exciting, because that's what will make or add value to the traditional engineering knowledge that we have been studying or we have been applying. So like I said earlier, this whole topic is about structural engineering being the backbone of the built environment. And we talked about bridges and dams and everything. When we say backbone, so if we are saying this is backbone, then obviously the backbone needs to be really strong to be able to hold up this whole body of infrastructure. And for that strength, it should come from us, from engineers, both in the academic, in the profession, and also in the people who develop the tools for their use. So let me just be a little bit kind of philosophical, if you may allow me for a few minutes to be. What is this all about? What is this structural engineering all about? If you look at it from a very, very simplistic manner, it is all about cause and effect. There is a certain cause and there is an effect. And our job is to find these relations in between the cause and effect. So basically, cause, which could be a natural cause or a man-made cause, which is varying with time, always varying with time. Even the static loads, so-called static loads, are varying with time. And then actions, which could be force, which could be a displacement, and effect, which could be deformation and stress. So basically, if you look at it, we are just playing with or looking all the time working within this broad definition of cause and effect. And we are just always worried about what are the causes, what are the effects. And the biggest question in this cycle that is the effect acceptable? And that's where the problem starts. Problem in the sense that the building codes come in, regulations come in, public comes in, everybody has a different perspective of what is an acceptable effect of the cause that we are talking about. And then the difficulty lies in these 5 areas that you can see here. And that's where we spend a lot of our time. That's where we differ between each other. First of all is how to define the cause. How do you determine seismic hazard level? How do you determine wind velocity to be designed 10 minutes, 1 minute, 1 hour, 1 year? What return period to use? At what height should be measured? People will debate on that forever. And building codes will disagree on that forever. Same is the case, how to determine the actions from these causes, analysis, structural analysis, hand calculations, slide rules, tools, software, no software, intuition, whatever you want to do. There needs to be some way to link the cause, or we need to analyze the effect of that cause somehow. And that's again the second, where modeling, assumption may be different, modeling type may be different. So much can go wrong and so much can differ in that. So right at these two steps, we already start to diverge a lot between different people, different building code, different, I would say, schools of thought, and also different times over the progression of our profession. Then how to determine effects on structure due to these actions. Next step is these actions are there, how to determine the effects on the structure, how to establish acceptability of these effects, and finally, how to make sure that the effects are acceptable. So if the effects are not acceptable, the deformation is too large, acceleration too large, stress too large, what do we do about that? And what about the structures which have already been built? What are we going to do about those where we find that the effects are not acceptable now, because we have a better understanding of the causes, or better understanding of the relationship between causes and effects, because our knowledge is changing all the time. So I always ask this question in every sort of talk, that if all the building codes that we have, they differ because of this, which one is correct and which one is not correct? All of them cannot be correct. If you follow simple logic, if there are 4 answers to a question, only one can be really correct. So either none of them is correct, or any one of them we don't know. So that's the first issue with the code that many people take now, that you don't know, that because they differ so much, and they differ on very basic things. The quantity is as simple as the creep rate or creep coefficient. Such wide variation. Concrete is concrete. It's going to creep on a certain rate. Why there is such a great difference between the codes and the creep rate? It's hard to understand that. And similarly, on many other things, the codes would differ on very basic parameters that you would think would be identical, because it's a property of the object. And I often also ask that if there are 2 buildings you designed, one to British BS code, one to ACI code, and there's an earthquake, will the earthquake know the difference between which building is designed on which and apply the forces according to that code? Of course not. It's just going to apply, the building is going to respond the way it's going to respond, irrespective of whether we designed it, we didn't design it, we followed a code, what code we follow. It's going to respond based on what is there at that time. And that's, I think, why the performance-based design has the ability to determine the performance of what is actually built or to be designed. So this is the problem with the acceptability and all of the process there. Then acceptance criteria are different. How much deformation, rotation is acceptable? Somebody is saying that many radians, another one is saying that many radian. We can't agree on that also. So this is the difficult part in our profession that makes so much difficult, otherwise simple task. And then you have seen this progression of our design understanding or design approaches over the time as we learn. The first one was intuitive design, as our speakers talked about, the same guy is an architect and a builder. So it's a master builder concept. They design and build things without any calculations or mathematics. Yes, they took 30 years, lives of maybe 100 people, of 1,000 people, but that was intuition. There was nothing else available. Then codes came in and start to help us to codify things, tell us what we can and cannot do. Not only tell us what we can and cannot do, also told us how to do it. The procedures are also written down. And then people start to follow, but then we don't know what do we get in the end. Is it good or not? All you can say is, yes, I followed the code. If you ask me a question, is the structure that I've designed is safe or not? I cannot answer that. All I can say is, yes, I followed the code. Ask the people who wrote the code. They will, but again, that explicit answer wasn't there. So that is the code-based design. Then led to the performance-based design, where we are now, in this phase, many people in different phases talking about performance-based design in various aspects. And then the next stages that some people are already working on is the consequence-based engineering or the risk-based engineering, because performance itself is not enough to the people who insure your building. They would like to know the risk involved, even if you follow or you don't follow the performance. And they don't care about what earthquake or what concrete strength. They just want to know what's the risk of this building not being damaged, so that they can charge the premium accordingly. And then finally, the resilience-based design, looking at the things in a big picture, not just the structure. Look at the community, look at the society, look at the work that people are doing. Because as you know very well, if a building is damaged, even partition walls, and people have to shut it down, businesses go out of business. People cannot live there anymore. People's lives change. I've especially mentioned about all these earthquakes that we see. Earthquake in Nepal, I was there immediately after that. We went to a condominium building. It was very well designed by good engineers to the code. And the structural members were all there, not really damaged, but all the partitions were broken, walls were falling down, building was completely inhabitable. So people spend their lifetime saving to buy apartments there, which they cannot live anymore. So the building is designed to code, but who can explain it to the people who lost their houses that, I'm so sorry, I followed the code. So the resilience of the community, resilience of the society, so resilience-based design is which now, everybody is aiming towards, and people are demanding that we should go, structure engineers should think beyond their building or structure, because the building and structure is the backbone. So if the backbone is injured, it's not just the backbone which is injured. The whole body is no longer able to move. It's a paralysis that people have. So the backbone, if you say the structural engineering is the backbone, then we must ensure that our structures, which are the backbone of the infrastructure, should not only stand by themselves, but also make sure that the rest of the body, which depends on it, also stands up. So that's where our profession is going. So wind currently is locked on the code-based design level, although in China, they're also doing performance-based design of wind, some talk there. Earthquake has gone to performance-based design, wind is catching up, and earthquake is moving towards resilience-based design, and other hazards will catch up too. So that's what you can see where we are currently and where our design approaches are going. So we need to teach all of this at some point to the engineers or to our profession to be able to do that. And if you look at it again one more time, if I may take step back, it is all actually a game played between a few variables. It's like a tic-tac-toe kind of a thing. You cross that, you divide that, you divide that. There's just a few variables that we're dealing with, not a lot. There's just the length, there's a mass, there's a force, there's time, there is displacement, stiffness, damping, energy, and resources, and then everything else is drive. All of the time, structural engineers spend their life trying to find relationship between them. One is known, other is calculated, other is not known, and we are just trying to get one from the other. And Professor Murthy's presentation in the morning also talked about 5 important things. So we are just working around playing a game between these things at one time or the other, because there are no more other quantities to compute. And of course, the resources that we use there in that one. So if our problem is not that it doesn't look that complicated, because there are few things that we have to deal with, we should be able to understand them very well. Physical meaning, their relationships, if we understand them very well, we should be able to tackle them effectively. We shouldn't have to spend, in my just intuition, we shouldn't have to spend as much time as we spend on these design problems after so many years of experience, centuries of experience. So there is another interesting document prepared by CTBUH together with UNESCO, and they said, especially related to tall building, but it applies to other disciplines also, that what are the 5 or 6, 7 things in future which will be very important for the profession or for our development to continue. And you can see this list: real-time structural monitoring of completed buildings, validation of modeling assumptions for wind and earthquake, improve the protection from multi-hazard events, design criteria to determine acceptable levels, and development of holistic performance-based multi-hazard design analysis of buildings. So you can see that this research also leads to similar thinking, that in future, these are the 5, 6, 7 areas where our profession needs to work. Now, then the question is, are we transferring this knowledge or skills? Are we preparing our engineers both in practice and to be added to practice in these areas? So then the question comes, how are we going to do that? If they are going to do all of that and looking at the way things are moving, how are we going to do that? I have no answer. I'm just going to ask the question. So please don't wait, hold your breath for the answer to that question. But basically, we need to develop a few skills, and our speakers have been talking about it. Understand the physical meaning, most important. Like just now we heard, we don't understand physical meaning of the things. Differentiation, you mentioned. We don't understand what is integration, what is differentiation. What are the really physical meanings of all the items that we do? What is really damping? How can you explain damping? Or we talk about energy in the building all the time. What does it really mean? Virtual work, if it's virtual, it's hard to understand something which is already virtual. But how do we understand all of that? So understand the physical meanings, establish relationship between the quantities that I mentioned, somehow, intuitively, physically, philosophically, whichever way, but understand those relationships. Why this equation is like that? Stiffness equation, why is it like that? Then simulate and visualize. This is very interesting, important, and easy. We must be able to simulate and visualize these relationships and these things if we cannot physically see them. Then create efficient configuration based on all of that. And we have talked about very good presentation by how you can do these parametric generations of all of the configurations by intuition, by simulation, by parameterizing, by whatever way. So, the 876, if I'm correct, it's the designs that they produce for that building is an amazing amount of work that the computers can do. But we should still be able to get to that number by our own intuition to some extent. And then communicate, and that's where we lack completely. Especially as structural engineers, my students, everybody, we cannot communicate what we do to the public, to other professionals. And I'm going to leave it there because I know that Ashraf is going to talk a lot about that. So I'm going to not step on that particular, but this is the most important, I would say, lacking in our profession right now. So let me show you another pyramid, this time upside down, which is the learning retention. Now, when we were developing a new program online, which I will talk about in a minute. So we took that program to our academic senate, and they said, this program is online. You don't have lectures in the class. But if you look at that, that has the lowest retention of any medium of learning, only 5%. The rest, next one is reading, then audiovisual, then demonstration, then group discussion, practice, and finally teaching. So that's how much retention you can get from various activities or of learning. So if that means that when we talk about how, we should actually look at this pyramid and see where we should spend most of our effort so that people can retain what they are learning. And that brings me to this small simulation, because I'm talking about simulation. And I'm going to continue with Professor Penning's morning, that video of the apparatus that he carries in his class everywhere to show the interrelationship between the mass natural period and the oscillation. And we can do the same thing. We don't need to carry that apparatus anymore because now we have tools to actually simulate the same effect. So we have this waveform, and it excites the first mode, small building. Second waveform excites the next mode because the resonance is over there, and third can excite the next one. So we actually can easily simulate all of those physical things that can make. So just an example that we can, that is obviously having that apparatus is great. But what we can add here to this one is not only motion simulation, we could also add stresses that we could not show otherwise in a physical model. We could add bending moment, we could add shear forces, we could add other parameters that we can also visualize or simulate using this simulation, and which can help us to understand the relationship between ground shaking and the natural period, or whatever things relationship that we want to understand. So this will bring me to the next important thing that I want to emphasize. So simulation and visualization is the key to improving the retention. I'm sure, when I remember from my bachelor degrees, I only remember one lecture very clearly. after 30, 40, 30, 37, whatever years. And that was that my professor, late professor, he came to the class, strength and material class, and he was carrying a piece of foam that he probably cut from his mattress. And he had drawn on it the horizontal and vertical lines, and he brought in the class and he bent it, and he said, see, plane section remained plane after bending. And that stuck in my mind forever. And I think most of my work, I wrote a book recently on cross-section behavior, is probably connected to that lecture. And I wrote some software also, CSI call other programs, all about section behavior. So probably that somehow stuck in my mind badly, because that was a nice, he showed it very clearly, physically, that the place. So we can do all of that now with simulations. And that's why I think we have the opportunity to go in that direction. So some of the initiatives in that direction, I want to just talk about, tell you two of them, basically. The first one is that we can see that there is a demand for an ecosystem for connecting learning and employment. I think this is very clear. People want to make some, if they learn, they would like to utilize it to generate, money or living from there. That's very basic. Learning philosophy is great, but it's much better if you can apply philosophy and also get paid for that. So this is important, that we connect the learning with earning, as there's a very famous book right now going on called Learning and Earning. So that is, I think, important, that the experience is connected. So that's what brings it to lifelong learning, and speakers have mentioned about this is the importance of lifelong learning for everyone. And the continued professional development, CPD, programs are everywhere. Every country has a law that engineers, to continue their license, must get some certain CPD points. So they are always looking for programs to attend where they can gather those points and continue to be licensed engineer. So this, I think, is the key where we can work on, and people who did not have the opportunity in the past to learn through those things that we are talking about, it's not too late, because we still can do that right now. And in AIT especially, being a university, like I mentioned, we have this cycle going on in our work of creating knowledge and disseminating that knowledge. Because we have, just to be very narrow on structural engineering, we have a wind tunnel, which is a good tool to have to understand wind effects and test those. We have a structural lab where people can experiment, create things, destroy them, break them, see them breaking, measure them, all of that. We have, obviously, a teaching and research infrastructure, and we also have AIT Solutions, which has a lot of projects that we get to work on, interesting projects, and very specialized projects. We don't do design work, normal design work, we never undertake. Only something which we feel is interesting, we are interested in that. So that, together with our collaboration with CSI, which, as you can see, is one of the partners in this event, who are developing the tools, and to be able to access that sometimes, then we say, okay, is a great thing. And with our lot of partners, many of you are here, we have this ecosystem that helps us to create this knowledge that benefits everyone in this figure. So based on that, we have created a platform called AIT Share, and we will be launching this. Actually, this was developed by our team, our IT team, in-house, and this is a knowledge sharing and learning platform, and it will be launched next month. It is still almost there. Basically, the idea is to share this knowledge with the profession and other people. And I'm going to invite anyone who would like to put up their talk or lectures over there, and we have a mechanism to make it worth your while also. So that is the basic platform, and on that platform, the first major initiative is this one. We are launching this August, is the Professional Master's Degree in Civil Engineering, focusing on design of tall buildings. So why this particular program? Because as I mentioned, we have the whole ecosystem for this particular field. And we believe that, okay, all of that, we should make it available to the professional engineers. But professional engineers don't want to leave their job, obviously. So it is 75 to 80% online. We still want them to come to AIT once a semester for a week, because First of all, you need to say that I studied in AIT. If you say I took a course in and we've never been to AIT, it's not really an AIT degree. But beyond that, our academic senate will not approve the program unless they come to AIT for some time and actually take the final exam there. So for 2 reasons, we have that provision in the program. And I'm so glad for 2 reasons. Now, one is that many of our speakers present today have kindly agreed to be on the advisory panel of this interesting program. So it's like a new things, and many of you are already part of that program. Many of these speakers are already on the advisory panel, including Ron Plavenzik, who could not be here. I also invited him, but he is busy elsewhere. So this is our first a group of advisors for that program. So they're, as you can see, professionals, practitioners, academicians, and all, and architects as well. And second, so that's one initiative that AIT is doing. Second one initiative that maybe Ashraf is in a better position to talk about, but I just want to mention it, is the CSI initiative on developing tools for both learning and application, because they are very, very good at doing this, for developing tools for professionals. But how about adding, rather than a black box, how about making it gray box, not a white box, but a gray box, which is semi-transparent, so people can actually access some of the things which are going on, play around with that, and also make it a learning experience. So two platforms are now being developed, actually already developed, the CSI Cloud platform and the CSI Mobile platform. Both of them are now already launched, and they will be expanded further to provide both learning as well as professional. This is the suite of the apps, mobile apps, which are there. Some have already been released, and the next set will be released gradually. And on that, you will find 2 interesting ones, a faculty assistant and a student assistant. The idea is, and I have tried this, one of the things, again, in a university you get to do is, you get, with due respect to my colleagues and students, you get cheap labor and guinea pigs to test your ideas, and also to do research on things that may or may not go anywhere. So we used these apps in my course last year on advanced concrete design. So the idea was that all of the assignments will be done through mobile apps, and no paper and no submission of any kind. So I have an app called Faculty App. The students have an app called Student App. And then I will send an assignment to them, to all of them, and they have to use multiple apps on their mobile phone to complete one task. So from one app, do some calculation, do some thinking, put it in the next calculation. So it's a continuous process, not a black box. It could have been easily solved on a single app, but we didn't go that way. We divided the problem into 5 steps, each step on a different app. So because they're on the phone all the time, no matter what you do, so might as well be doing something useful with that time and play around together with all the other things, play with the apps that we have created for them, because they are graphically quite fun. And at the same time do their assignment. And I found that to be very engaging. These apps have discussion groups. I've watched them discussing with each other the assignments. So discussion, visualization, practice, and doing something that it makes learning better and more fun, at the same time provides more understanding. The next one is pen and paper, which we will, instead of pen and paper, probably pen and tablet is the next best thing. So the next apps that we are having are tablet only, so that people will have to draw or do something, use their pen and pencil in that context, so that you can start sketching, and only that we will accept. So in my class, I never accept any paper for many years for any submission. It has to be completely paperless, all of the work. And this helps to go in that way. I don't want to talk about saving the environment and trees, because it happens, but that's a byproduct. So another way to learn is machine learning and AI as a learning tool, because we can use this to develop the sense of the things quickly and cross-check our design, or like a guessing game. You can play a guessing game like Watson. It's like this is what do you think it is? and you say it's a number. Let's say we give you a question that what do you think the column size of a 40-story building with 10 meter by 10 meter grid should be? And you say, okay, 5 meter by 5 meter. And the program said, wrong, because for machine learning, it would have already learned that that's not the right answer. So you then play that game with this, and then you can learn. And you say, okay, 0.8 meter, yeah, that sounds something right, or something like that. So this machine learning tool can actually become a kind of a learning because it has all the answers learned from previous projects. So we can use the machine learning to do that. And of course, even do a real job of quickly giving Jojo the estimates or finding what is the wall thickness it will work in the end, because it's based on previous experience. The next one, the last of my slides, I talked about the learning from the instrumented buildings, learning from the actual buildings. And this is something that is, number one on the list that I showed you from CTBUH. And that is what we are also actively doing. And a lot of you are already involved in that, putting sensors on the buildings, on structures, and getting the data. So that means we have a real scale test lab in the real world and get the data from there, learn from that, calibrate your model, see why your natural period computed by ETABS is 2 seconds or 4 seconds, and actual observed period is only 1.5 seconds. Why? What happened? What can I change the model to get the same natural period that I observed or measured from the building? So learning from the response of the instrumented buildings or instrumented structures will be another way going forward. So with that, I think, let me come to the last question is, do we still have a job in the future? This is an interesting question, future, are we still relevant? And this is a website that, which says that if you go to this website, it says, will robot take my job in the future? And you can enter your job description and tell you what is the chance that in future the robots will take over your job. So just for fun, I went there and I entered any accountants or auditors in the room, and it said 94% chance is that your job will not be there in the future and you're doomed. And then I said, okay, let me try computer programming, not software development, computer programming. There's a difference. So I said computer programming, and it says 48% chance that your job will be taken over by robots. And now I'm getting really scared because now next I'm going to try civil engineering. And then I went for civil engineering, and it says totally safe. Less than 2% chance that your job will be ever taken over by a robot in the future. So that's the good news. So all we have to do is keep learning, and we'll be okay. Thank you so much.